schedule of assignments, and I apologize. So I have not gotten the calendar function going, and I deeply apologize for this. It takes a long time to do all this stuff, but everything, all your assignments, you can understanding, that's when you want to email me or set up an appointment with the tutoring center ASAP. So, and then so labs will also be posted there. So we don't have like a lab manual, but I'll just post these labs by week. So today, well, half of you are have lab today, half of you have lab on Thursday. So we'll be doing the popcorn lab. And normally I would want you to do pre-lab questions for your lab section. I'm not going to really post that this quarter. I would highly encourage those who go to the lab appointment to familiarize yourself with what you're going to be doing. But again, I'm not going to be explicitly checking this, so if you have questions about kind of go from there. And then so labs also taking paper copies of those notes we do kind of when you are labbing. One on Tuesday, and one back on Tuesday. We have on Thursday, one back on Thursday. And again, I'm usually flexible with due dates, plus or minus 2 days. But I really encourage people to stay on top of the work. It's chemistry. Build up, it takes a lot of time, and you don't have to all the time. Lana. Adrian. Izzy. All right. Good for y'all. Y'all are here, and I don't normally take attendance in class, but I kind of expect y'all to come to class. Let's talk about chemistry. So some of you have taken chemistry before, so that's good. I don't know the level of chemistry that you took in here, but you have chemistry. in.
I'm sure there's a way though.
Yeah, I'm assuming it's a little metal. What else do we have? No, fertilizers. And then also pesticides, so all that. Yeah, about it. And so this was now published a while ago. And so it was originally published back just can't. And like, for example, a lot of it, I don't want to go like down the rabbit hole, but a lot of chemistry, and this is my opinion, is when I get home, you kind of have to play games. So that means based off, I'll go with what you see. So, those qualities, definitely. So it's based off what you see, so this could be like color, smell, gas evolution, any other things you can notice, or visual. between a theory and a law? And it's kind of crazy to think about, like, germ theory is really just a theory, right? So we have a lot of evidence to isolate viruses and bacteria. So we kind of, it seems like this is the way things are. That, microscopic bacteria and germs that we get infected with, that's what makes us sick. And so that's germ theory. But different evidence came along that we could disprove germ theory and come up with a new explanation. smaller than millimeter. What's the next guess? Yeah, so it's a micro. It's not a micrometer scale. Or 1 times 10 to the negative 2. Now what about 30 light years. But I like, so light years, notice, right, that's how long it takes light to travel in a year, so that's really far. And or to write this out in kilometers, I don't even know. 4, 13. That's how many kilometers. So that's pretty crazy. So then the next question is, well, how do we write, represent all these? And so we have scientific notation. More clearly what a mole is later, but mole is going to be a base unit. Then length, we have meters, mass, grams, volume. times 10 to the 9th meters. These relationships, so like so this is just a different way of showing you what was in the chart. So we have 1,000 millimeters is equal to 1 meter. So if you look over here, so that's what it's saying over here. So 1 millimeter is 10 to the negative third times your base unit. And so you could have also thought of it. 1 times 10 to the negative third meters is equal to 1 millimeter. And so it's up to you whether you want to use these negative conversion factors. Again, I like to keep things positive, just from my mind, and I'm not looking at like a little negative and then I drop it or something. So let's do practice here. And so that cancels, that gives us what we're looking for. That's my first step. Now let's go grams to kilograms. Our new conversion factor. Look, kilo, now 10 to the third. That means times our base unit, 1,000 grams. The one-step method, if you just immediately saw, okay, I know that it's 1 times 10 to the 6 milligrams gives me 1 kilogram. Again, from that factor, because milli, 10 to the negative third, kilogram, 10 to the third. So you can see you have 10 to the 6 difference there. And then we could have just set it up in one step here. So 600 milligrams. Kilograms, 1 times 10 to the 6 milligrams on bottom, and so that's the exact same thing we have up there, and so that should also give you that same answer. So whatever way works, I always encourage the two-step method, just because again it's kind of easier for people, it's laid out on the chart, but you can see, and then just set up your conversion factor kind of step by step. Yeah, so that would be, actually typed it in there. Yeah, it would just be 600 because I could do both. So we could do divided by 1,000, divided by 1,000. So either way, I can get that same answer. Okay, any questions so far? Do you need more zoomed out? Pause for a second. Yeah, I'll post it. I usually don't post notes after every class. I usually wait till like the week. But if you really, really want it today, if you remind me, I'll try to export them. Okay. Yeah, you want to do that ASAP. So, we can chat after because I don't know the numbers on this section off the top of my head. But yeah, we'll get you in the lab. All right, other questions? So we'll do some more practice. I just look for like showing your work, that sort of thing. And it's best, kind of the more work you show me, the better chance you have of getting more points. So if you just give me like a fraction answer or whatever, I can always interpret that and, translate it. I don't necessarily look for like a specific unit. That's why you should always label your units, right? So I know what you did. Yeah, but I'm not trying to like overly penalize people, but I want to see like the math, the steps, and at least a somewhat correct answer. If your final answer isn't correct, calculator errors do happen, but that's why you want to show step by step. So you can be like, everything looks good, just they punch something in. And that happens a lot. All right, so now we'll do some more practice. So now let's look at significant figures and measurements. And this is super important. And so you'll get a sense of this once you start being in lab more and manipulating things. And so we have this thing called significant figures. And reporting of significant figures is an answer that is dependent on the precision of measured values given in a problem or determined by the precision of laboratory glassware. And so in a problem, right, they give you the number of sig figs, but what you're really thinking of, that's reflective of whatever they did. So when you go to lab, right, you weigh something on the scale, and however many numbers it spits out, that's your sig figs, right? So that's how accurately that balance is capable of measuring. And then we'll also look at different volumes, again, how you read that, and again, that's why you have to use the appropriate glassware for whatever you're doing. You don't want to be trying to do analytical chemistry with glassware that's not going to give you enough detail. And then, so when we're looking at these sig fig rules, you'll also learn, so conversion factors are not treated when we're trying to figure out how many sig figs we need to report. And again, this will all be clear as we do practices. But these are just considered exact values. So if you were doing a conversion from inch to centimeters, you would not count this as sig figs. So you would, or else we would lose all our sig figs and only report to one number. And so let's go through these rules. And again, it'll all make more sense once we start doing stuff. And so we have our significant figure rules. So the first rule is, and this is pretty easy, so all non-zero values are significant. That makes sense, right? You get a number, it obviously matters. So in this case, we have 536. There's 3 digits, so this has 3 sig figs. Then the next rule is zeros between non-zero digits are significant. And I usually call this the captive zero rule. And again, this kind of makes sense. So if you have numbers before and after a zero, that zero's not really doing anything, just hanging out, being a number. And so in this measurement, 6,703, we have 4 sig figs. So 1, 2, 3, 4. So all those digits matter. And then, so our leading zeros. So these two numbers, let's actually combine these. So we have these next two rules of leading zeros and trailing zeros. And so let's kind of read what it says and then we'll summarize. So it says, placeholder zeros to the left of a non-digit zero are not significant. So if you look at this, we have these 2 zeros here, but what they're really doing is they're showing how small. And so in this case, these first 2 digits are not significant. These are the only 2 significant numbers since they're non-zero, and so that would be 2 sig figs. And then with our trailing 0, 1, we see, so zeros to the right after a non-zero digit are not significant. So if you have 7,000, looks like a large number, only 1 sig fig. And then this number, so 32,040, so that captive zero, so we have a captive zero that is significant, But then this last one is not. So this would be 4 sig figs. And so the way to summarize these two rules is if a 0 is showing how big or small, it is not significant. And so the other way to kind of think about these and help you is if you can write it in scientific notation and get rid of the 0, it is probably not significant. So for example, this 7,000, we'd want to go ahead and rewrite it as 7 times 10 to the third. So that's our scientific notation. So we just have our number. We would have a decimal point and other numbers if there were. But now we can clearly see, right, we just have 1 sig fig. And then kind of the advantage of scientific notation too is, let's say you did want to say, well, I can measure accurately on this 0. And so maybe you have 2 sig figs. So what you could do is 7.0 times 10 to the third. So how many sig figs would this one have? So 2. And we haven't quite. And so if you look at this, we have zeros to the right of the decimal point are significant. And so if we're adding zeros, so right, these zeros aren't showing how big or how small. All they're showing is accuracy. So if you're going out that far, if you're reporting, that's saying, yes, our equipment is measuring this far, and I can measure this digit. So these are showing accuracy. And so again, with the 7,000, if we wanted to show, depending on how accurate our measurement is, so we could do 7.00 times 10 to the third. So now we have 3 sig figs. And 7.000, let's say they were all significant and we wanted to show that. So now we know we have 4 sig figs. All right, let's try some practice and see how we fare. So look through these examples. So I'll give everyone kind of a minute or two. Write down your answer, how many sig figs are in each one, and then we'll go over them. So let's start with number 1. So 54,000. How many sig figs? You can, yeah, show your hands. So I see a lot of twos, excellent. So 2 sig figs. So remember those last 3 zeros, they're just showing how big. So they're not significant, so 2 sig figs, excellent. You could also rewrite it, right? 5.4 times 10 to the 1, 2, 3, 4 to really show, yes, there are only 2 sig figs. What about 304? Let's see some fingers. So I see threes, excellent. 3 everywhere. Okay, number 3, we have 0.000000210. We see some fingers, so I see some 2s, see some 3s. And so don't forget about this last 0, right? So all these were not significant, they're just showing how small. Well, then that last one, the fact that they bothered to report that, that means that it's accurate. So, yep, 3 sig figs. Excellent job. Question?
So that would be 2.10 in scientific notion then?
Yes.
You heard that. Okay.
Times 10 to the 1, 2. Yeah, so times 10 to the negative 6. So what about this next one? So 4,500,000. So 2. I see a bunch of 2 fingers everywhere too. Excellent. So 2 sig figs. Again, we can rewrite it. We want to emphasize the 2 sig figs. And then what about this last one? Let's see if I tripped y'all or not. 2, 2, 2. No one fell for my trap. Excellent. So 2 sig figs. And so I wanted to point this out. Again, y'all did a pretty good job. No one really fell for it too badly. But if you see this in a textbook, so you have 10 and then a decimal point, that is indicating that yes, it is significant. We often don't write it like that because it's kind of confusing. It's, you know, and you're like getting out your magnifying glass, like, is there really a period there? And so it would be best to write it, even though it seems kind of silly, right? 1.0 times 10 to the 1, just so you know, okay, that is 10, and I do have 2 sig figs. But just be aware of that. Textbooks still use that, where they just put a period at the end, and you're supposed to know that it's 2 sig figs. All right, I think we can get through temperature at least. And so now let's look at our temperature scales. And so like I mentioned, chemistry is usually in Celsius. And temperature is one of those funny things where, like, I have no idea what a normal degree range in Celsius is, but chemical reactions, I know what they should go at Celsius. And so if we kind of compare our scales, if we're looking at Fahrenheit, so you may be aware, so our freezing point for Fahrenheit is at 32 degrees Fahrenheit. And Celsius, they made it nice, easy numbers. And so water freezes at 0 degrees Celsius, and then water boils at 100 degrees Celsius versus 212 for Fahrenheit. And then we'll also look at the Kelvin scale. And so the Kelvin scale is based off of absolute 0. So does anyone know what absolute 0 is? Excellent. So absence of molecular motion. And this is really crazy because what this is saying is your electrons will stop moving, because we'll later learn, even though, right, this solid piece of podium looks really solid, there's all these electrons moving around, and so there's always movement. But if we could get to absolute 0, and so absolute 0, it's just kind of this theoretical point. They've gotten really, really close. I would have to look at the current literature to see where they're at. But obviously, absence of molecular motion, that's absolute 0. And of course, that's really hard to do to thermally isolate something. So you'd have to look into the research. They have all these like contraptions set up to try to isolate it and then get it down to that temperature. It's really quite fascinating. But so that's what the Kelvin scale is based off of. And so absolute 0 is 0 Kelvin. Again, absence of motion. But what's nice about the Celsius and Kelvin scale is they scale the same way. So your temperature Kelvin is just equal to your temperature in Celsius plus 273 degrees. And you might see it 273.15, but usually I leave off the 0.15 unless you see like a specific homework example where it's like exactly, convert exactly 1.00 degrees Celsius to Kelvin or something crazy like that. Most of the time that 0.15 doesn't matter, and I'm not looking to penalize you. And then, so here's our conversion for going back and forth between Fahrenheit and Celsius. And so you just need to be able to look at this formula and plug things in. So of course, we could plug it in. If we were given it in Celsius, plug in our Celsius here. So times 9/5 plus 32. And then you might also see a different version of the formula. So notice if you see like 1.8 times your degrees Celsius, that's the same thing. So you might see that depending. And then going from the other way, notice that this is in parentheses, so you would start with your temperature in Fahrenheit, do the subtraction first, and then multiply it by that 5/9 factor. So let's just do a quick conversion. So convert 443 degrees Fahrenheit to degrees Celsius. So I'll give everyone a minute or two, try it out, plug it in. So do we have any volunteers for the answer while I plug this in? Yeah.
I got 228.3 continuous.
So 228.3, other people get that?
Yep.
Excellent. And so let's talk about sig figs, because we're just dancing around there. And so we haven't quite gone over how to do the math with it. But then, so we were given 3 sig figs in our problem, so 3 sig figs. So this doesn't count as part of the sig figs, right? That's just our formula. And so then once our calculator spits out this answer, we want to report it to 3 sig figs as well, because we're doing our multiplication division. So we can report this to 228 degrees Celsius. And again, we'll go over the rules and stuff later. Yeah.
So if we put a decimal point after that, then it would be wrong. Because
In that case, I actually don't think it'd be wrong. It'd be funky, yeah. But yeah, you wouldn't want to do like 228.0 like that, then you have too many sig figs. And let's see, we have like 5 more minutes left, so let's get through this at least a little bit. And so, a very common way to examine a piece of material. So let's say you have like an unknown material. You could look at its density. So density, we're gonna later learn. So we have intensive and extensive properties. So do you have any guesses of what's what? What is intensive versus extensive? Yeah.
I'm going to assume that intensive are interior properties and extensive are exterior properties. Or wrong?
You're like kind of right, but I want a little more clear. So what do you mean by internal?
Like density would be a internal property, right?
So I'll put does not depend on substance amount. And I'll put inherent. Hopefully that makes, I'm just trying to be a little more clear than like internal. I totally know what you're going for. That's like, it'll always be the same. And so density is an example of an intensive property. So if you have a piece of brass, let's just say, it will always have the same density, right? Or a piece of zinc. Zinc is always going to have that same density. It's just you're going to be dividing different numbers, right? So, and let's just define extensive too. So extensive then does depend on the amount of whatever substance. And so an extensive property, that would be like mass, so how much is there, length, volume. So all that depends on the amount. But then if we go back, so let's add more things to intensive. So intensive, this also includes like melting points, boiling points, so it doesn't matter how much of a substance you have, like water always has that same boiling and melting point, whether it's like an ice cube or a huge vat. We could also do hardness, so thinking about how hard rocks are, color, state of matter, so solid, liquid, gas, and texture. We could go on and on, intensive. And so let's go back. And so density is just this ratio of mass to volume. So density equals mass over volume. And I'll just go ahead and rewrite it in this little triangle trick format. Are y'all familiar with the triangle trick?
Nope.
So the triangle trick kind of tells you like what you need to do mathematically depending on what you're trying to solve. And so we'll do this example problem together. Although this one's kind of easy. So it says if 73.2 milliliters of a liquid has a mass of 61.5 grams, what is the density in grams per milliliter? And so notice you set up the triangle with, and this works for any formula that's set up like this. So mass goes on top, density and volume here. And then, so in this question, it's asking for density. So you can just think, cover up that whatever you're looking for. And then it tells you what to do. It tells you to divide mass divided by volume. And let's say you were trying to solve for volume, right? You would cover up volume, then you just do mass divided by density. Trying to solve for mass, cover it up, density times volume. So that's a little triangle trick, but you can also use your dimensional analysis and everything to help you. And we're kind of out of time, so let's just do this first example, and we'll leave this for next time. And so in this case, We just have to plug it in, so density equals mass, so 61.5 grams over 73.2 milliliters. Notice that density is given in units of grams per milliliter. It could also be like kilogram per liter, etc., but just some mass over volume. And then, of course, let's plug that in and get some numbers. So 61.5 divided by 73.2 spits out this number, but then we have how many sig figs? 3. So then we want to report 1, 2, 3. We can't round that up or anything, so our answer is 0.840 grams per milliliter. All right, so we'll end there today. And I will post the lecture notes also online, or excuse me, a link to the lecture. If you guys want the lecture notes today as opposed to waiting to the end of the week, just let me know and I'll export them. Okay, it sounds like people want that, so I'll try to export it after class. And then if you snuck in, make sure you check in with me so I know you're at least alive and still planning on being in this course. And then I will see half of you later on in lab in a little bit.
Okay, a few days I haven't very much for it, and still kind of bit worried because I also have my math class to deal with. Also take a lot more time because of the difficulty and also a lot of time to be able to understand the process of control or I'm able to pass math class. The same amount of time. I'm not really too sure if I'll be able to keep up with all the process in the long run.
Well, I mean, you can always sign up for things now. I was glad to forget when the raw day is.
Okay, yeah.
But I would encourage you to just try it all, you know, in front of the tutoring center. Just be there every day.
Yeah.
And then
Well,
with
I
the
just go to tutoring center after class, but I usually leave like before 1:30.
And then, were you here, did you check in, did I call your name?
No, I got
Yeah, this is my first day of class, so I'm not sure. Yeah, so I should keep the schedule of my name in Spanish time, but I always go by B.
Oh, okay, so I already got it.
Yeah, I'm not sure if I should keep the schedule or if I should adjust the schedule because of the work I have to do in the long run. That's kind of what has me worried.
Personally, I would just try to like sign up for everything now and then knock it out if you can. Again, if it becomes too much, you can always decide then which class to drop.
Okay, because in the long run, I may need to drop a class so I can keep up. No, I need to pass these classes for sure, and I always let my mom know about that. So should I probably cover that? Maybe we can discuss things a bit? Because I think that may be the best option, really, to let her know of the plan. Because after all,